Yep.
Have you not noticed?
Okay.
I remember where I sat there and I made a big deal about it because I was so mesmerized. Well, you were probably.
All right. So probability of dependent events. We looked at probability of independent events, which was basically you're going to multiply, if you're rolling a dice, 1 6 times 1 6 times 1 6, however many you got. So today we're going to look at dependent events. And for dependent events, our rule's going to be different. So we already know that probability of A and B is probability of A times probability of B for independent events. Okay, so for A and B for dependent events, I'm trying to get this out because I know what that first one is, but probability of A times probability of B for that. Let me get out my notes here because what do I have? I don't remember what I put in that second blank. No, it's going to be probability. Sorry, this is probability of A times probability of B given A. I can't remember what I put in that second blank. And I don't have it. Maybe I do. Yeah, oh, there it is. Or it can be the other way around. So it could be probability of B times the probability of A given B. It's not nearly as difficult as it seems. Okay, now we can think about this. For independent events, we could really use these same rules because if A and B are independent events, the probability of B given A. You all right, Brandon? All right. Do you need to go call? You sure? You're not going to spread it to the rest of us? Okay. Okay. So probability of B given A is just probability of B because A does not affect B at all. This is like saying, what's the probability that you roll a 6 on a die and you flip a heads on a coin? So those two don't affect each other. So your probability of flipping a heads, given that you got a 6 on the coin, is still just the probability of getting the heads. It's just 0.5, right? It's just the same because that coin, the die had nothing to do with the coin. So this rule really applies in both cases because this is not affected. The rule for dependent events can be used for all probability of A and B situations. I'm using a new symbol here that I don't believe I've used with you before. If you have a upside down U, that is a symbol that means and. So you could possibly see that somewhere on the exam or something. So if you see that upside down U, that means and. Just for your own knowledge there, if it's a U, that means or. Just a regular U. It's the union, which means or. Upside down U is and, which looks a little like an A. Okay? All right. So here's an example. You draw 2 cards from a deck without replacing them. What is the probability that you choose a king and an ace? Okay? So this is an example of dependent probability. So the probability changes from the first card to the second card because you don't have as many cards you're choosing from if you don't replace them. So the probability of king and it really should probably say what's the probability that you choose a I don't guess it matters. King and ace. Okay, so this is going to be the probability of getting a king times the probability of getting an ace given that you got a king on the first try. So what is our probability of choosing a king out of the 52 cards? We got 4 out of 52. And then what's the probability? 52, not just 5. Then normally the probability for an ace would also be 4 out of 52, but we've already taken one card out of the deck. So for the next one, it would be 4 out of 51 because there's one less there. So if you multiply those two together, you're going to get 0.00603. So likelihood's fairly low there. All right, questions? All right, you choose 2 cards from a deck without replacing them. What's the probability that you choose a 3 of hearts and another heart? Okay, so how many 3 of hearts are there in the deck? Just 1. So your first probability is 1 out of 52. And then, let's say that we do get a 3 of hearts on the first draw. What's the probability that we get another heart? How many hearts are there? There are 13 hearts. There are 13 hearts, but we've already picked one, right? So that means we've only got 12 left out of how many cards? 51, because we have 1 fewer card in the deck than we did before. So if we multiply those two together, we should get 0.0045. Yep, so that stuff I wrote down the other day, you might need to review. Here, let's click quickly. Probably not going to. We're way out of time. Way out of time. But 52 cards. You might want to write this down if you don't know cards. In a standard deck, you have 4 suits, which are hearts, diamonds, spades, and clubs. If you already know it, you don't have to write it down.
Okay.
We're writing this down for all of you out there that are not card sharks. So, that don't. Red are hearts and diamonds. Black, spades and clubs. 13 cards in each suit. And those cards are ace 1, or ace 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, king. Anything else I need? Right now, my cards is pretty much it. In general, they go in that order, although depending on what game you're playing, aces can be high or low. Sometimes aces are higher than a king. Sometimes they're counted as a 1. Sometimes you get to pick which one it is. It will tell you one way or the other, or it should. If it doesn't ask me, I'll tell you. If it doesn't, it's because I've overlooked it in a problem. Okay, questions? All right, so a lot of the problems you're going to get are going to be card problems for this because it's just something that we can use for describing this really easily. So, let's go back here. I'm just going to type this. I can type better than I'm right, probably. You have a closed basket that has 11 black socks and 8 white socks in it. What is the probability that if you randomly choose 2 socks, you will get a matching pair? Assume all the white socks are the same. Do laundry like my husband does. Assume all the white socks are the same. Assume all the black socks are the same. Doesn't matter if they're the same size. Doesn't matter if the toes are the same color. Just if they're both white, they go together. That's how he does laundry. If he ever did it, anyway. It's been a long time since he did it. But so all right. So what is the probability that we will choose, if we choose 2 socks, you will get a matching white pair? Okay. So we would have to choose a white in the first place. The white would be 8 out of how many? 19. That's how many total socks you have. Then you would multiply that by 7 because we chose one of the white socks. So there's only 7 white socks left. Out of how many socks are left in the basket? 18. Okay? And so whenever you multiply those together, you should get 0.164 for that. So if you're going to go with the random method of pairing socks, you got about a 16% chance of it working out for you. Now my son, he would just pair any 2 socks together. It doesn't matter the color or style. Have you ever done laundry here? There's never an even number of socks. They disappear.
Okay, you don't worry about that.
There's never an even number of socks. I have a whole basket full of just mismatched socks I can't find the match to. And as soon as I throw them away, guess what happens? The match shows up to the other.
Yeah, we have a table in our house. This here.
Yeah.
There's socks.
Yeah.
Random socks.
Yeah. Yeah. If you have ever done your own laundry, you know this. There's never an even number of socks. Yeah. Yeah. This morning, and my son's very particular about his socks. Well, he's very particular about what type of socks he wears. So he does have a few pair left in his drawer that are matched. I didn't fold clothes this weekend, so I have washed some things, but they're still in laundry baskets, I must admit. But so he won't wear those that are left because he doesn't like them. So he'll just he'll get dirty ones, or he'll just get 2 that don't match. Boys. Okay. 2 students are randomly selected to represent our class in a survey. What is the probability that one girl and one boy will be chosen? Okay. Now this one's a little bit tricky, and here's why. Okay. So whenever we're looking at this, if we're looking at this class, let's just go with the people that are in this class, like actually physically present right now to do this. So we've got 5, 6, 7, 8, 9, 10, 14, 15, 16, 18 of us, I think. 18 students if we don't count me. Is that right? 19. Okay, 19. And we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 boys. All right, so the probability that we choose a boy would be 10 out of 19. And so that means there's 9 girls, but it would be 9 out of how many? 18 there. 0.263. Okay, and I think I really should change the wording on this, that one boy and then one girl will be chosen. I think. All right. Okay, what is the probability that 2 girls will be chosen? So we'd start with, we've got 9 girls out of 19. What would we multiply that by? 8 out of 18. .211. Okay, and then our last scenario is what's the probability that 2 boys will be chosen? So for the 2 boys, we've got 10 out of 19, and we'd multiply that by 9 out of 18. It is the same, isn't it?
Wow.
That's kind of, that only worked because of the numbers that we have in here. So that's kind of weird. All right, so let me check something. Okay, so now notice I did change the wording up here because really, I guess if we looked at part A as it's worded here, if it was the probability of 1 boy and 1 girl, we'd have to really do 2 probabilities there. We'd have to do, because this is the probability of getting a boy then a girl, but you would also need to look at the probability of girl then boy, because both of those, if it was worded like it originally was worded, and you would have to consider both of those, either boy then girl or girl then boy, for that. So I'll try to, if it's 2 girls or 2 boys, it doesn't matter, because there's just, the order doesn't matter because they're both the same. But okay, let's look at the next one. For each example, state whether the events are independent or dependent and tell why. Okay. All right, so what you're going to do for this is you're going to use the rule. So probability of A and B is going to equal the probability of A times the probability of B for independent events. Okay, so slide this over here. So in this case, what you're going to do is you're just going to test to see if they're independent. So the probability that somebody plays basketball and the probability that somebody is female are both given here. So if those 2 things are independent, then the probability of A times the probability of B is going to give us the probability of A and B. So the probability that someone plays basketball times the probability that they're female will give us the probability that they play basketball and are female. So for this one, you would test 0.15 times 0.5, and 0.15 times 0.5 is going to give you 0.075. So does that equal the probability for both? It does not. So that tells us that these are dependent events. And you could imagine, like, it may or may not be true at different schools, but there, might be typically more boys that play basketball than girls, especially if you're looking in, like, Maybe not as much in high school because you pretty much just have the teams, but if you're looking at like elementary school kids, I know that, or for soccer anyway, every time that Hunter's been on a team, there's a few girls, but there's not as many girls that play those sports as there are the boys, typically. So if you knew, like if you're looking for the probability of basketball and female, it's not going to be the same. It's just those are not independent events, because if you do play basketball, you're more likely to be male out of that crowd. So, so those could be, that could be the reason that those might be dependent events. Now, probability for number 6 here, you're looking at the probability of a tails on the first toss times the probability of a tails on the second toss. Just by what we've talked about, you guys should know that this is these are independent events. Flipping a coin does not affect, but because they're giving you these numbers, you need to test it. So if you do 1/2 times 1/2, it does give you 1/4. So these are independent. Okay, for 7, we don't even know what the two events are. They're A and B. So we would just test it. We would say 0.2 times 0.13, and that's going to give us 0.2 times 0.13 gives us 0.026, which tells us that these are independent. And so for X and Y, if they're independent, we can just multiply their two probabilities. So 0.75 times 0.27 equals, so alright, so we've got 0.2025. That is not the same as 0.25, so these are dependent. Okay, questions there? Okay. In a shipment of 20 computers, 3 are defective. 3 computers are randomly selected and tested. What is the probability that all 3 are defective if the first and second ones are not replaced after being tested? So, typically whenever you are working in an environment like where they're producing something like a computer, you would not test necessarily every single thing that comes through the line. Maybe computers more so than other things, but if you're producing chewing gum, I'm sure they have safety tests that they do like every so often to make sure that everything's good for the certain standards and you don't have any. A lot of times there'll be like salmonella contaminations that they detect before anybody ever actually gets sick, because they're doing this like safety test on stuff. So that doesn't mean that they're safety testing every pack of chewing gum that comes through the line. They're probably picking, every 5 hours we go check this. So this is kind of, like a realistic, what's the probability that you'll actually catch the ones that are defective in this case? So here, how many computers are defective? 3 out of the 20. So that's the probability that you get one of the defective computers for the first computer. All right, so that leaves you 2 defective computers out of how many? 19. And then 1 defective computer out of 18. So 3 out of 20 times 2 out of 19 times 1 out of 18 is going to give you, I did something wrong there. What did I do? Oh, I guess it's right. I don't think I did anything wrong. You guys getting like 8.77 E -4? Alright, so we're getting 8.7719 E -4, which is scientific notation. And scientific notation means 8.7719 times 10 to the -4, which means that we need to move the decimal place 4 places, so it'd be 0.0008779. So, with this method, it'd be very unlikely for you to pick all 3 of the defective computers. Okay, and so the next question is also an important one. We know we have a nearly impossible chance that we actually pick all 3 that are defective. The other thing is we want to know, like, what's the probability that we don't find any of the defective computers and they all get through. So in this case, you've got 17 good computers out of 20. Then you'd have 16 out of 19, and then you'd have 15 out of 18. Okay, so 17 out of 20 times 16 out of 19 times 15 out of 18 is going to give you 0.596 there. So you got a almost 60% chance that you wouldn't catch any of them if you were doing this. So if you knew you had that many, like if somehow you knew you had that many defective, you'd probably need to check more than 3 computers because you're not catching that many of them that go through. Okay, questions? Okay, another thing you can think of right here, so unless you're terribly suspicious looking, the airport screening is supposed to be random. So what are the probabilities that you get picked? Like, you might have 100 people in the line. You might have 3 of them with drugs in their pockets. But you are not you're not gonna catch everybody that comes through there, because they don't necessarily go. I mean, I'll go through the screening. Hopefully, they can catch weapons a little more easily. But something like drugs might be harder to find. What's the probability that they catch it? Whenever you see when you see shipping containers coming over to our country, they have to go through customs, and there's all kinds of things they check for. Of course, they're checking for drugs. They're checking for there's also things that are just not supposed to come over because it might bring, we don't want stink bugs. Stink bugs are not native to the United States. You never saw a stink bug when I was growing up. They're everywhere now. So they look for stuff like that.
Oh, yeah.
I've heard that, but I don't know if it's actually true. Yeah, ladybugs were bronzes. Maybe so. Yeah. Yeah, brown ones are taking over. I don't know. Alright, but as things go through customs, they don't check every single piece of everything that comes into this country. So they don't catch everything. But they'll catch, hopefully, enough to scare people into not doing it, right? They won't catch every speeder going down the highway. But they catch, hopefully, enough to scare people from speeding a little bit. All right, so last one. For 11 and 12, assume there are 375 students at Elkin High School. All right, so this is important. So about 8% of Elkin High School students walk to school. If 2 students are selected at random, without replacement, what is the probability that they both walk to school? So the first thing we've got to do is we know we have 375 students. We have to figure out what 8% of that is. So to find 8% of 375, you're just going to multiply. So you'll multiply 0.08 times 375. Okay, so we'll have 0.08 times 375 is going to give us 30. And thankfully, that's an even number. If it was not an even number, I just round to your nearest whole number there. So that means that 30, you have a 30 out of 375 chance that you're going to choose a walker the first time. Okay, then you would have a 29 out of 374 chance that you choose somebody that walks to school the second time. So whenever we multiply those together, 30, what have you got there? 0.006 for that. Okay, questions? All right, last year, 72% of Elkin High School juniors, who are now seniors, scored above the state average on the ACT. I think that was an actual statistic. I can't remember what year it was, though. It's been several. So it was not this past class. In a class of randomly selected seniors, what is the probability that all of them scored above the state average on the ACT? Oh, we do need to know that. Let's just take 375 and divide it by 4 and see what we're close to. I should. 93.75. So let's go 94. We're just giving it a rough estimate right here. We're only looking at one class. Okay. All right. So let's say that should be information I should have given you though. So let's add that in there. There are 94 seniors. Let's add that in. Okay. So 72% of them scored at or above the state average. So 94 times 0.72 is going to give you 67.68. So 97 times 0.72 gives you 67.68. Let's just round. We can't have 67.68, so let's round that to 68. I'll try to make sure on a test that you don't get one that you got to round like that. So if we want to know what's the probability that all 5 of the randomly selected seniors scored above the state average, we would have 68 out of 94 times 67 out of 93 times 66 out of 92 times 65 out of 91 times 64 out of 90. Okay, and so that gives me I'm going to go 190. If I round it 3 places there, you get 0.189905. Okay, questions? This is a lot like your independent probability. You just have to think about how it reduces each time you choose something. Okay, so